Okay, so we are up. We are recording. This is a data set of about 3,000 people. That, come on, you. Well, maybe that's not going to work. About 3,000 people where we have items measured on a lot of different scales. So we're going to do a factor analysis of this, and we're going to look at it a few different ways. We're going to look at it so that it is completely wrong, and then we will work our way backwards from there. The first thing that we have to decide on when we're doing a factor analysis, at least in this approach, M plus doesn't give you this option, which is nice, but is whether or not we want this to be a principal component analysis or a straight up factor analysis. What is the difference between these two?
In the PCA, the assumption is that all the variances are unique, and in the regular factor, it's shared variance.
Yep, we're only looking at shared variance in a factor analysis, and that is not just shared variance between two items on a single factor. It's every potential factor that's in there, right? Looking at all of the shared variance across all of the factors. Principal components looks at, let's do this, display variable names.
Could you put the SPSS window full screen?
Yeah, it's trying.
Oh, okay.
That's what this black is here.
Apologies.
This scale is the UPS scale. Has anyone ever used the UPS scale? I'm sorry. Whoops. Oh, I had the right button. This is the UPS scale is a scale of impulsivity, urgency, negative urgency, positive urgency, sensation seeking, lack of perseverance, and lack of premeditation. And so it is a 5-factor scale. I'm going to draw it up here in just a second because it's actually been condensed. It's technically not a 5-factor scale. And I'll explain what I mean by that in just a sec. It's actually 7 factors. But that's because we have 2 higher order factors within this. All right, got these moved over. So the UPS is a scale that looks like this. We have a whole bunch of items up here that comprise negative urgency, positive urgency, premeditation, perseverance, and sensation seeking. And of course, these are driven, or these come from these things, and looks kind of like this, and each of these represents individual items in the actual questionnaire, right? And you can imagine that it's that way all the way across. Of course, these things are correlated. This oftentimes is correlated at a rate that would be absolutely ridiculous. But all of these things should be correlated. Similarly here, 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 like such. Man, this marker smells terrible. All right. And so we have these 5 basic factors, right? It's been supported over and over and over. We know that this is a 5-factor scale. And then, actually, there are 2 higher order factors that are driving these scores. Those 2 are correlated. So technically, we have 7 factors, right? But within these 7 factors, the ones that we're primarily interested in are these first 5. Unfortunately, this is a structural equation model way of looking at factor analysis. You don't get that with the non-structural equation model way, like the OLS way. But okay, so we have identified that we've got these items, and we want to analyze these items and determine what the factor structure is of these items. This is easier to do when it's already been done once and you know what the factor structure is. Let's pretend that we don't know what the factor structure is, and we've got these 50, how many items? 59 items, and we want to see what it is. So as far as factor analysis description, or descriptive statistics, we want the initial solution. Univariate descriptives are less important. If you select that, it's going to give you the mean of every single item, the standard deviation of every single item, skew and kurtosis of every single item. Right now, we don't care about that, right? That's less important. Correlation matrix. The correlation matrix is important because the factor analysis is actually done on the correlation matrix, right? And it's trying to identify items that seem to be correlated together because some underlying factor is driving responses on those items. And so in principal components analysis, it analyzes a correlation table with the assumption that on the diagonal, everything is 1, right? There's 100% variance within a given item, and then across, underneath or above the diagonal, whichever you prefer, the variance is only looking at what's shared. In contrast, if you're doing an actual factor analysis, the assumption is that along that diagonal, there are no longer ones, right? They are 0.5, 0.4, 0.3, whatever, the actual amount of overlap of that item with every other item in there. And so, what is the rationale between the difference is between PCA and factor analysis is that PCA is using 100% of the variance, but what is the rationale behind PCA versus factor analysis? Why would you choose one over the other?
Is it based on theory?
It is based on theory, right? It's going to be based on theory, and it's somewhat based on the idea that, at least for factor analysis, we're just not interested in error, and we're not interested in variance that can't be accounted for by the factors that we're looking at, right? In truth, that unaccounted for variance, at least in this context, is all considered error. It's not necessarily all error, right? There's going to be some variability in responses that is not just due to method, but is due to the fact that some of those responses are probably driven by external factors that we have no idea what they are, right? But anyway, let's select coefficients, and we don't need to worry about the rest of these. We definitely don't need to worry about significance levels at this point. And then let's go to extraction. This is where we're going to select whether we're going to do principal components or factor analysis or any other sort of interesting way of looking at this. I'm not going to go through all of these different ways. Principal components is this, obviously. Principal access factoring is this. We are going to be primarily interested in principal access factoring, but for demonstration purposes today, we are going to select principal components to start with. We also want to know, we want to see the scree plot. We want our unrotated factor solution. We are going to extract factors based on an eigenvalue that is greater than 1. And this is almost always what you're going to select if you're doing exploratory factor analysis. Because you're saying, like, I don't know what factors are there, so we'll just say as long as it has an eigenvalue of 1, we're going to roll with it. What is an eigenvalue of 1 equivalent to? It's equivalent to 1 standard unit of variance. And in principal components analysis, 1 standard unit of variance is 1 item, right? And so if you're saying that you can explain the variance of 1 full item, then we're going to use that. If we can't, if the factor can no longer explain the variance of one full item, then we're not interested in that factor anymore. And that's not saying that it explains the variance of a single item. It's saying combined, a factor can explain the variance of one item, right? That means that it could take 30 items, each one explaining 1/30th of the variance by a single factor. But it does wind up being the variance of one full item. All right, let's hit continue. Let's go to rotation. For right now, we're going to do no rotation. We have a couple of options here. Varimax is a type of rotation that is orthogonal. The two most common here are Varimax and Promax. Varimax is an orthogonal rotation. What does that mean?
They are not uncorrelated.
Yeah. So if we draw it out, right? If we just assume two factors, and we have a bunch of items here, and a bunch of items here. If we do no rotation, right, then we're going to get the factor loadings for these on a factor way over here, and the factor loadings for these both on this and on this, and of course you'll also get them for this as well, right? So you're going to get two different sets of factor loadings, and these wind up not being that far away from these in this sort of instance, right? You wind up saying like, oh, well, this data seems to be related to this factor in almost the same way that it's related to this other factor. And similarly, if you see these and these, although I didn't draw these lines the best, you will say like, oh, well, this data seems to be related to this factor in roughly the same way, or not quite the same way, as they're related to this factor, right? So you see that there are long lines and long lines, right? And that's what is that called in regression when we draw a line? If we've plotted a line through there, and then we look at the distance between where our observed data is and that line that's plotted through there, we call that residual, right? Yeah, so all of these actually are an attempt to minimize the residuals between those things. Now, we have the same data, and we rotate those factors. So we have all of this data like this, we have all of this data like this, and then we say, actually, we're going to shift this factor this way. And similarly, we're going to shift this factor by the same magnitude, right? This way. What we do is we minimize the residuals for this factor, right? From this data to this line. And we actually increase the residuals from this factor, or from this data to this factor. And so what you'll actually see when we do a rotation is it will give us our initial factor loading, sorry, for an unrotated factors. And when you rotate those, you'll see that those factor loadings change pretty dramatically. In the initial step, for unrotated factor loadings, you'll see an item that might load at like 0.4 on this factor and 0.4 on this factor. And when you rotate it, it goes to like 0.8 on one factor and 0.02 on the other factor, right? So rotation allows you to minimize residuals and really zero in on how this, or where these things are linked to a factor. And then of course we have the last piece of this, which is if these factors are correlated, and almost always they are, you see data like this, data like this, and you shift this one in a little bit, right? And you also shift this one in a little bit. You're allowing those factors to change interdependently, not dependently, and so you wind up with factors that are at least can be correlated, right? Like as this one changes this much, this one might change this much. Yeah.
So is this an oblique rotation?
This is oblique. Yep. This is an oblique rotation. Yep. So, but for starters, we're not going to do any rotation. Let's look at loading plots. Hit continue. Scores. Yeah, we can save the variables also. And so what will happen with this, if you save the variables, is you will get a person's actual score on a given factor, right? And the idea is that we have some sort of amount of sensation seeking, and some people score higher and some people score lower, and this will tell you what that person's average score is for sensation seeking on that factor based on all of the items that they've got. And then, oops, so hit continue, and then options, just leave it as exclude cases list-wise, that's fine. All right, so let's run this. Please don't go wonky on me.
What type of rotation did you pick?
There's no rotation. We're starting with no rotation. Let's see if this will stretch out. It's working a little bit. View, can I make this at least medium? Did that change at all?
Can you drag the left pane over? Like where it says output log, like you can minimize.
Just get rid of that? Is that what you want me to do?
And like the little blue bar, you can like drag it to the left.
Oh, this guy here. All right. Oh, I hate SPSS. All right, so I'm just going to click in here and then scroll through. Oh, there we go. So, oh, that went fast. Let's scroll back up here. We looked at, we used principal components, right? And the first thing that we're going to look at is our communalities. Communalities is the initial amount of variance that we're starting with, and in principal components, we're starting with one unit of variance, right? Because we're looking at 100% of the variance in each item. And then extraction is how much of that 1 unit of variance is accounted for by all of the factors that we've extracted here. And it's not just the few factors that we're selecting, but in this case, it's all of them. So for the first question, the first item, I have a reserved and cautious attitude about life. We can see that our initial variance is 1, 100%, and we were able to account for 40.2% of the variance in that item, right? And you see this similar pattern rolling down here. Now what's interesting, and you'll see this when we move over to factor analysis, is for the most part, you always start with an initial amount and the extraction is always less. However, there are instances when the extraction winds up being more. Anyone know what that's called? You never see it in principal components. It will never be more than 1. But in factor analysis, you will see when we are able to identify more variance than what there is in an item. Anyone know what it's called? All right, we'll talk about it when we see it. In SPSS, you almost never get an error message. In M+, it will give you an error message when that happens. All right, so here are our total variance explained. We start by getting eigenvalues, and so we have initial eigenvalues, percent of variance, and then the total eigenvalue, and then this is the cumulative variance that's accounted for, right? And so our eigenvalues are right along here, right? Or right along here. These right now are exactly the same because we have 0 rotation, right? When you do a rotation, you're going to get initial eigenvalues, and then you're going to get the eigenvalues for the rotation. We selected that we were going to extract factors based on whether or not the initial eigenvalues were greater than 1. And so in this case, we see that we can account for 56% of the total variance in all of the items. And we have how many factors? 8. Now, one of the things that I mentioned in the video is this rule of thumb of 1, and I said that there are some problems with the rule of thumb of 1. And what was one of the main problems with the rule of thumb of 1 for eigenvalues?
It excludes values that are like 0.9. So
Yes, so we have like a 0.96 here, right? And that means that it almost accounts for all of the variance of a single item. And what we're saying is we're arbitrarily deciding that that doesn't matter, but 1.04 does matter. Now, we do this in stats all the time anyway, right? We arbitrarily decide that 0.05 matters. And so the question is, do we really need to arbitrarily decide that this matters or doesn't matter? What should guide that? Yeah, always, right? And so with factor analysis, this is why exploratory is problematic, but it should always be somewhat guided by theory. Even when it, I didn't mention this at the start, but what is the primary kind of function of factor analysis today? Anybody know? What is it mostly used for?
Skill development?
Yeah, test development, actually. So, yep, scale development, absolutely. So, but anyway, so here we see that we have 8 factors that have been extracted. And this is problematic because there are only 5 factors in this data, right? And for some reason, we're coming up with 8. Why are we coming up with 8? Who wants to take just a random guess?
Because you're not rotated.
It's not rotated. That is one. And also, we're allowing a lot of bleed over, right? So we will get to a point where it is rotated and where we don't have bleed over. But let's scroll down here and yeah.
what do you mean by bleed over?
I mean that other items wind up. Yeah. So other items wind up having a illusory association with a higher order factor, right? Oh, yeah. So I drew these higher order factors on here, right? And the idea is that these items should be accounted for by this factor, and this factor should be accounted for by this factor, not the actual items that are up there. And so what you wind up having is a bunch of items that aren't related to this and are related to this. And it also has to do with rotation. I'm sorry, I call it bleed over. People, that's probably not the right terminology. But we wind up with more factors than what we should have at this point, right? Let's scroll down a little bit, and this is our scree plot. And the scree plot will give you a factor all the way up to the last item, assuming that there are 58 factors and each item makes up its own factor, right? Of course, the purpose of this is to try and condense 58 items to the kind of most necessary items to tap into a single factor. If you can ask 13 questions instead of 58 questions, you're just better off, right? Ideally, you're better off. All right, so based on this, we use this weird kind of old principle called the knee of the scree. And you've heard me mention that a couple of times. Who's heard of that besides from me? Who's heard of that before? Nobody's ever heard of somebody say the knee of the scree? All right. I suppose, though, only a few of you have ever done factor analysis before. All right. So what the knee of the scree means is the first factor is always going to account for the vast majority of the variance in a factor analysis, right? And the second factor will account for a large chunk of variance, and the third factor some. And eventually you get to a spot where the amount of variance that can be accounted for by adding factors switches, right? So you see this kind of nice drop here. We've got a lot of variance accounted for here, a fair amount here, a fair amount here, a fair amount here, and eventually we hit a knee where it doesn't matter, it kind of levels out, right? And that's what the knee of the scree is. It's the spot at which things tend to level out. So in this, I would say that the knee is either here or here, right? So we're talking about 1, 2, 3, 4, 5, or 6 potential factors. This is important because I said in the past, or I said that we know that this is a 5-factor scale, right? So looking at this, you could come up with 5 factors, and you could drop out 7, 8, 9, which are right along here, and that would lead you to 5 or 6 potential factors, right? as we scroll down a little bit further, we really want to get to a spot though where that knee is sitting at where the knee bends. You're sitting at an eigenvalue of 1, and the next eigenvalue beyond that is well below 1, right? That's the ideal spot if you're looking at a factor analysis like this. Unfortunately, this is not a strong, it's one of the things that we love in statistics is when we're able to have some sort of a threshold that we can say this is better than that, right? Like this p-value was less than 0.05, this one wasn't. Or this chi-square, was, we tested this model and we can objectively say that this model fits better than this model statistically. And you can't do that with factor analysis, right? At least not this way. Next week, you will be able to. But right now, you can't objectively say that one factor is better than another factor, or that one solution is better than another solution. And so oftentimes you're trying to make an argument for why 5 factors is better than 4 factors or 6 factors or something along those lines. And you don't have the nice discrete decision points that we often have in other aspects of data analysis. Okay, so as we continue to scroll down, we have the component matrix. This is the basic loadings for each factor. And so you can see like I have a reserved and cautious attitude towards life, tends to load on factor 3 here, right? Also, it loads a bit on 5 and 6 and negatively on 1. So if we try and look at our items and we say like, okay, well, what other thing tends to load on factor 3? We are ideally are going to find items that sound an awful lot like I have a reserved and cautious attitude towards life. This one doesn't, but I generally seek new and exciting experiences. Kind of sounds the opposite of I have a reserved and cautious attitude towards life, right? But it also loads much higher on factor 2. I generally seek new and exciting experiences. Now the odd thing is you also see that this loads highly on factor 2, which is I generally like to see things through to the end is how that finishes. Those two things don't seem related at all, right? Yeah, and so this winds up being one of these higher order issues where things are kind of bleeding over. All right, if we continue with 3 though, let's see if we can find another item that seems to be consistent. My thinking is usually careful and purposeful, and that is negative on 1, but it is positive on 3, and that sounds an awful lot like I have a reserved and cautious attitude towards life. I like to stop and think things over before I act is how that question should be ended. And you can do this with all of them, and sometimes they seem to jive very nicely and sometimes not, and this is because we have higher order factors in there and our things are not rotated, right? And so something that would be roughly an equal distance over, so if you have an item that winds up falling, say, here for this factor, it might have a reasonable distance from both of those when our factors are unrelated or uncorrelated. Once we correlate those factors, it becomes much closer here and much further, well, assuming that one is there, much further there, right? All right. So let's keep scrolling through our component matrix here. This is the component plot. It just shows components 1, 2, and 3. It doesn't show all of the components, and they never do, but it's going to show like the 3 biggest, and it's really not worth looking at, to be perfectly honest. Oops. Component score coefficient matrix. This is very similar to the coefficient matrix that we saw up here. These are the actual standardized coefficients, though, and the one above that is unstandardized coefficients. And that is basically it. Component score covariance matrix. I don't know what that one is, to be perfectly honest. All right, so based on this, what would you conclude? What would you conclude about, there are kind of 2 main things that you can conclude from this factor analysis or this principal components analysis, and that is how many principal components are composed, or do these data compose? 8, roughly 8, right? You can make an argument for 9. You could also make an argument for 5 or 6 based on the knee of the street, right? How much variance do the initial 8 account for? 56. You can also use that as a way to make a case for 5 or 6 factors, because we're looking at 50 for 5, 53 for 6, and if we go all the way to 8, we're only gaining 2% more variance. It may not be worth that additional 2%. Of course, the problem with all of this is we have not rotated the factors, which we will do when we come back. So let's take a break. When we come back, we will rotate these factors and see